For this coursework we had to design a wing that surpassed the given parameters. As the only material choice was foam board, we were limited to making a main load-carrying rectangular spar. In order to reduce the weight, we decided that we should either make the thickness decrease at one point, as the root was at highest risk of breaking. Alternatively, we could have cut holes into the sides of the spar. However, that idea got scrapped as predicting the properties would have been significantly harder. After that, we decided to make small models in order to see what would be the best way to fold the material. In order to know what dimensions the spar needed to be, we needed to finish the spreadsheet that was given to us. After finding suitable dimensions in the program, we made our first test spar, which was used in order to see if any of the calculations or given material properties were wrong. When we tested the root direct stress, we learned that our spar's compressive strength was 1.9 times stronger than the given value, and so we corrected that in our spreadsheet. Following that, we attempted to do the torsional test. However, the spar would simply break before any angle was produced. This was most likely caused by the fact that the spar had already failed, weakening it, and the large polar moment of area the spar had. Finally, we had started to do the shear stress test. However, the force required to break it was very large, about 20 kilograms, so from that point onwards we simply assumed that it would never experience such a force. When we made our second spar, we made it as tall as possible. This is due to the relation between width, height, and second moment of area. This time we modelled the spar, along with the rest of the wing, in SolidWorks. This gave us a better idea of how the final design would look. However, we made a mistake. We simply assumed that the torsional strength, like the compressive strength, was also significantly larger than the given value, so when we checked the spreadsheet output we ignored the fail in the torsional angle. This time we did the torsional test first, which it failed, twisting 11 degrees. So we checked the spreadsheet and found out that both the calculation and torsional modulus were incorrect, so we corrected them. Following that we tested the root direct stress, passing it, breaking to tension at 800 grams, which was expected. After taking into consideration everything we learned, we made our third and final design. Our spreadsheet said that our spar would pass all tests, although for torsion we would be cutting it close. This meant that it was our limiting factor, and any ideas to save weight couldn't be done as it would weaken it torsionally. For the torsion test, our spar twisted by 5 degrees when 0.43 Newton meters of force was added. For the bending moment, our spar broke at 1200 grams. The fact that it took so much mass to break our spar meant that, even when considering our safety factor, it was stronger than it needed to be. But this extra strength was required in order to resist a torsional load.
Okay, yes, it collapsed. Okay, yeah. Okay, nice.
The spreadsheet says that it should have failed at 4.45 Newton meters. However, in the experiment, the wing failed at 5.4 Newton meters. This difference was caused when we tested our first spar. We took the lowest possible value for the ultimate compressive strength to err on the side of caution.